This is Elementary Statistics, practice test number 3, module 3, and here's chapter 7, estimating parameters and determining sample sizes. True or false? The confidence interval estimate of the population mean is constructed around the sample mean. Simply follow the formula. By definition, x bar plus minus e, where sigma of x bar is sigma over square root of n, e is z alpha over 2 sigma over square root of n. Part B, estimation means assigning values to a population parameter based on the value of a sample statistic. Everything is about the population based on sample. We'd like to have access to population parameter. We don't, we use sample statistic. And in this case, we make up a confidence interval. The confidence level is denoted by 1 minus alpha. Sometimes we call it 1 minus alpha times 100%. The maximum error or margin of error of the estimate for mu based on known sigma is given as E equals Z alpha over 2 sigma over square root of n. Sometimes they just call it Z. The parameters of T distribution is simply df, degrees of freedom, which in many cases it's equal to simply n minus 1. What criteria are required to apply the T distribution to make a confidence interval for mu?
The sample must be a simple random sample. Either the sample is from a normally distributed population or n is less than or equal to 30, population standard deviation.
N is larger than or equal to 30.
Yeah, sorry, population
Sure.
standard or deviation. Sigma is unknown.
The point being, when sigma is missing and everything else is in order, we use the T distribution. That's why it's important for you to read the question very carefully to see if sigma is given or missing. Now we want to find the value of the for T in a case of a T distribution with a sample size of 20 and a confidence level of 95%. And in the other case, when the sample size is 30, confidence level of 90%. So let's see how we tackle the problem. Number one, when we have a confidence level, in this case, 95%. So we put 95% in the middle. In this case, 95% is in the middle. And then 5% in the two tails. That's why you see alpha divided by 2, or in this case, 0.05 divided by 2, which is 0.025 on each side. So degrees of freedom is n minus 1, which is 19. Here's the T distribution table, or at least a portion of that. Here's the T distribution. On the left side, you're looking for degrees of freedom. In this case, number 19, you locate that. Then you go to the top, either area in one tail, in this case, in one tail should be 0.025, or area in two tails, it has to be 0.05, which means that one, when you put the two together, you come up with this answer. And because it's a confidence interval, you have two values, plus, minus 2.093. That's how you read the table. Now, in the case of the next part, sample size is 30. That means degrees of freedom is n minus 1 or 29. Confidence level is 90%. So if we change this to 90%, then this becomes a 0.1 divided by 2, or 0.05. So the total area in two tails would be 0.1, and in one tail is half of that. So first and foremost, you find degrees of freedom, and on the left column, you find that 29. Then you go for area. In one tail is 0.05, in two tails is 0.1, and you see this number, so plus minus 1.699 is the answer. Now, as far as technology is concerned, I'll show you one of them. For example, the second one. Okay, so we go with t-distribution, find the t-score, second vars or variables, inverse t. So we are going to put the area of a 0.05. Okay, area on the left side is 0.05. Degrees of freedom is 29, and that gives us negative 1.699, of course, more decimals. And because we know we are dealing with the confidence interval, plus minus. That's how you use the technology in this case.
Okay, so we have our TI-84 Plus Silver Edition calculator on. We're gonna select second vars, that's second vars. Then we're gonna select inverse t, which is number 4. I'm gonna move to number 4 and select enter. And then for the area, we're looking at the area to the left. If you recall, was 0.05, which is right here. 0.1 divided by 2 with 0.05. And the degrees of freedom, we all agreed that is 29. And then I'm clicking on enter and enter again, and that is our result, negative 1.699, as we use the table. Same answer.
Find the critical chi-square value for 20 degrees of freedom when the area to the left is a 0.01. Well, here's a table. And here's the graph which indicates the area to the right. In order for us to deal with the chi-square table, you need degrees of freedom, which is n-1. In this case, degrees of freedom is given. You don't have to subtract 1. And we need the area to the right. In this case, the area to the left is given. So if the area to the left is 0.01, the area to the right is 1 minus that. So degrees of freedom is given. Area to the left is given. Area to the right is the complement of that. The total area, as always, is 1 representing probability, so 0.99. So take a look. We find number 20, and we find 0.9 at the 0.99 at top. Here's the area to the right. When we put these two together, gives us this number, and therefore we write chi-squared, which in essence is the chi-squared of the left. The right side is 0.99. The area to the left is a 0.01, is 8.260. If you look at the second case, n is given. N is 30. Area to the right is given. So we don't have to do anything about the area. It's the correct one because we need the area to the right. But degrees of freedom is n-1, and area to the right is 0.9. So let's put that together. So here's number 29, and here's 0.9. So on the left, column, you find the degrees of freedom. In this case is 30 minus 1 or 29. Here's the area, and therefore the answer is 19.768. So chi-squared of the right, chi-squared of 0.9, because the area to the right is 0.9. Remember, we always need the chi-squared with the area to the right. 19.768 is the answer.
A statistician is interested in estimating at a 95% confidence level the mean number of houses sold per month by all real estate agents in a large city. It is known that the population standard deviation is 1.9. A, how large a sample should be taken so that the estimate is within 0.65 of the population mean?
Perfect. Again, word problem. What is given? 95% confidence interval, CI, short for confidence interval. Population standard deviation is 1.9. Population, therefore sigma. And we want it to be within 0.65 of the population mean. That means E is 0.65. That's the meaning of it. Now, as you recall, the formula was confidence interval is X bar plus minus E. I'm reminding you sigma of X bar is sigma over square root of N. E is Z alpha over 2 sigma over square root of N. And look at this formula. If you raise it to the second power both sides, you get E squared. On the left, this is Z squared sigma squared over N, and you can solve for N. Z times sigma over E, quantity squared. We want N. We just plug in everything. We have everything from the confidence interval. We need to find the missing Z. Now, it so happened it's a common one. 95% confidence interval, that means 5% divided by 2, alpha divided by 2 on both sides. So 0.05 divided by 2 is 0.025. So 0.05 divided by 2. And it gives us the value of Z. Now plug in here, do the math. Now here's what's going to happen. This is the least number for N we need, and it has to be discrete. Therefore, even if it's 32.1, you must round up. You will always round up. You don't round it accordingly. Why? Round up. Because even if it says 32.1, that is the minimum sample size. And if you need 32.1 at least to be on the safe side, you can always go up, but that's the minimum you need. Now we want to find the 95% confidence interval if we know that the mean is 3.4 X bar plus minus E. This is X bar. So we are going to add and subtract E. So from 3.4, subtract 0.65 and add 0.65. Now, what it really means is that we are 95% confident that the true population mean is somewhere in between. We are 95% confident that the true population mean is somewhere in between.
A random sample of 20 female members of a health club showed that they spend on average 4.5 hours per week doing physical exercise with standard deviation of 0.75 hours. Assume the time spent on exercise for all female members is approximately normally distributed. What is the value of the point estimate of the population mean?
Again, word problem. What is given? It's a normal distribution. N is 20, X bar is 4.5, S is 0.75. I want to make sure everybody understands why I'm using X bar instead of mu, S instead of sigma. We go back to the question. A sample of 20 female members of a health club showed that those 20 subjects spend an average of 4.5. So this number goes back to that with a standard deviation of 0.75. Again, this goes back to 20. It does not go back to all to the population. Therefore, this is X bar, this is S. If you recognize that, practically you're done. The point estimate of a mu is always X bar. That means we have to start from somewhere, and we start with the sample mean, and then we extend it and we make up an interval. We want to construct the 98% confidence interval for the mean time spent on physical exercise of all such females, which means we are going to use X bar plus minus E again. However, in this case, E is T alpha over 2 S over square root of N, and S of X bar is S over square root of. So we use the T distribution. That's the key difference here. We want 98% confidence interval. That means alpha is 0.02. And again, 98% here, 0.02 divided by 2. That means 0.01 on each side. Degrees of freedom is N minus 1, because we are going with the T distribution. So it's 19. And we find this from the table or technology. And we're going to plug in to X bar plus minus E, where E is calculated as T alpha over 2 S over square root of N. Now let's plug in. We just found the T, we have the S, we have the N. Plug in and calculate the E with a bunch of decimals. And now that you have X bar being 4.5, subtract this number from it, add to it. That is the mean being between the two values. So this is 98% confidence interval for the mean time spent on physical exercises of all such females. That means we are 98% confident that the true population mean is somewhere in between. If we were to do this by technology, so we use the confidence T interval. T interval, we put stats, unless we have data. Sometimes we are given data, we can click on that. Stats, that means we have X bar, 4.5, we have S, we have N, and we decided to go with 98%, 0.98 for the confidence level. We're going to calculate that. And as it calculates, it gives us again NSX bar, the same value we had here. They're slightly different because technology uses normally more decimals.
All right, this is how you use your TI calculator. You would turn it on first. You select the stat, and then you select test. You go to the third option, tests, and then you look for T interval. You go down, and looks like it's option number 8 for me, and you can click on enter, and then you enter the information that are given to us. We have 4.5 for the X bar, the mean, and standard deviation is 0.75, N is 20, confidence level is 98%, we put 0.98, and then you click enter, and you click enter again to calculate. And as you can see, we get the same results as shown here.
Out of 500 randomly selected adults, 300 said they were in favor of the death penalty for a person convicted of murder. What is the value of point estimate of the population proportion?
What is given? We are dealing with the binomial distribution because there are two outcomes. We are for it or against it. N is 500. X is 300. What is the point estimate of population proportion? Population proportion is P. The point estimate for it is P hat X over N. It's always P hat. P hat has the formula X over N. And again, when you are writing the given, it makes it easy to follow, plug in. So we got the point estimate to be 0.6 or 60%. We are interested in finding the 95% confidence interval for this case. And the formulas are as follows. Instead of X bar, now P hat plus minus E, where mu of P hat is P. So sigma of P hat is square root of PQ over N. However, P is missing, we use square root of P hat Q hat over N. And E is Z square root of P hat Q hat over N. The reason we use Z, we are really approximating it by normal distribution. In essence, we have to show NP and NQ are both large, and then we can use the Z. And it's important to see that there's one approximation. We are going from binomial distribution to normal distribution. So we never ever go to T distribution because one approximation is bad enough. Because T distribution in essence is the approximation of a Z distribution or normal distribution. So that being the case, we are going to calculate this for a 95% confidence interval. We need the value of Z, and as you may remember, it's a common one, 1.96. And needless to say, when P hat is 0.6, Q hat is 1 minus that. So we calculate this, and we are going to add and subtract this number from P hat. P hat is 0.6. Subtract this number from it, add to it, results in the following. So we are 95% confident that the true population proportion is somewhere between these two values. If we were to use the technology, we use proportion. So one proportion Z interval. They're asking for X, for N, the C level, the confidence level is 0.95 or 95%. We have all the values, 300, 500, 95%. We do the math and notice again these two, very close. If you stop here, this changes to 1 when you do the rounding. Extremely close.
To use your TI calculator, you select Stat, then you select Tests, and you go down, look for one proportion Z interval, then click enter. You enter the information. X is 300, N is 500, confidence level is 95%, and you select calculator, and when you calculate, you would see the results very close to what we have here.
How large a sample is needed to be 99% confident that the margin of error is 0.025 for percentage of golfers that are left-handed if we A, assume that 15% of the golfers are left-handed based on a previous study?
What is given? We want 99% confidence interval. The margin of error, E, must be 0.025 maximum. And now for part A, P hat is a 0.15 or 15%. So let's look at the formulas that we've had here. If you look at E and square both sides, you can see that it becomes E squared, Z squared, P hat, Q hat over N. If you solve for N, you get N equals Z squared, P hat, Q hat over E squared. Plug in, needless to say, P hat means Q hat is 1 minus that. And confidence interval of 99%, that's another common value. So let's take a look at it. If confidence interval is 99%, Z is 2.575, plus minus, I want you to know that, if you are going with the drawing and the graph, plus minus. But the reason one is good enough because it gets squared up, it makes no difference. P hat is 0.15, Q hat must be 1 minus that. We are ready to plug in all of these values. So Z, replace it with 2.575, P hat with 0.15, Q hat with 0.85. What about E? 0.025 and square that. So I hope you see the importance of writing all the given. Plug in. Don't forget to put the proper numbers, their decimals, you're squaring. And again, you must round up. It doesn't matter, this is 0.6 or 0.1. It gets rounded up to the next number, a discrete number, 1,353. What if we don't have a prior information? In other words, if we go back to part A, P hat is given. What if P hat is missing? Then what do we do? Then we assume the worst, which means we assume P hat and Q hat are identical and they are 0.5. Remember, they must add up to 1. So we assume P hat equals Q hat equals 0.5. We have the same confidence level of 99% with E of 0.025. That means E is the same, Z is the same. So this number is the same, this number is the same. But what about this one? This changes to 0.5, this changes to 0.5, and therefore their product is 0.25. In case you see this formula, this comes from the fact that the product of these two is 0.25. That's how they arrive at it. Plug in, write it with a bunch of decimals, and notice this one is 2, but it doesn't matter. We go up to 2,653. What I want you to notice again, a couple of things. Number one, you round up in both cases regardless. Number two, this must be larger than this or we have made a mistake, because this is the most conservative estimate. When we use P hat equals Q hat equals 0.5, this becomes the largest, because when the sum of the numbers is fixed at 1, the largest product occurs when they are identical. It can be proved using algebra or calculus. Given n is 30, x bar is 80.5, s is 4.6, and assume normal population, find 98% confidence interval for population variance and standard deviation. Everything is given symbolically, so there is not much to write except use the formulas to calculate the confidence interval for the population variance. And then for this one, just take a root. By the way, many times they're just interested in that. I want you to know that, but we use this one. When we take a root, we get to the answer. So that's why I wanted you to be exposed to both. So the very first thing is, all right, when I look at this formula, I need N, I have it. I need S, I have it, okay. So what is missing? Chi-squared of the right, this is red. Chi-squared of the right, this is red. Chi-squared of the left, and I don't have those. And it comes with the 98% confidence interval. That means this is 98%. And on sides, I have 2% divided by 2. That means 1% on each side, or 0.01. So degrees of freedom is n minus 1, or 29, and 98% confidence interval gives us alpha of 0.02. And in the case of chi-squared of the right, area to the right is a 0.01, so we write this. We have 98% smack in the middle, 2% in both tails. In the left tail is 0.01, in the right tail is also 0.01. Bear in mind, chi-squared starts from 0 and goes to infinity. It doesn't have negative values like the z and t distributions. So here's the table. And remember, on the left side, we have degrees of freedom. And we are looking for n minus 1 equals 29. We find it. And then across, we need the area to the right. Area to the right. So take a look at what happens for chi-squared of the right, or this value. 29. Area to the right is 0.01. So the answer is 49.588. I'm showing you exactly how to use the table. Now, I want chi-squared of the left. This is chi-squared of the left. I need degrees of freedom, which is the same number, 29. I need the area to the right in order for me to figure out the value. And the area to the right is 1 minus 0.01, or just 0.98 plus 0.01. However you want to put that, and that results in 0.99. So we go back to the table. The left column, we look for 29. At the top, we look for 0.99. When we put them together, it gives us this value. And so 14.257 is our chi-squared of the left. And believe it or not, if you're using table, this is the most tedious part, taking the longest time. Now we just plug in. Replace the n with 30, n with s with 4.6. So we have the same numerators, but the denominators, put this number here, put this number here. Now, plug it into a calculator. There's not much to that. And that's 98% confidence interval for sigma squared. All you have to do, take a root of all sides. And this would be the confidence interval for standard deviation, which means we are 98% confident. The true confidence, the true population standard deviation is somewhere between the two values. All right, I want you to notice when we want to use chi-square, either we have to use a table or you use technology. If you want to use the technology, it's very limited, but I have something here, for example, this one. You can plug in the information. The degrees of freedom, if we go back, was 29. If we put 0.01 and calculate, gives us the answer with a lot more decimal. So I want you to see that it can only happen with technology in this manner.